Good morning. Welcome to lecture 10 of Thermodynamics of Materials. We actually stopped somewhere. In the last class, we could not complete this example. Another example of reversible process, that is evaporation of water. This I started, but there were some technical difficulties, so we had to interrupt. And we actually now take up this one and finish this, then we shall go on with our next topic. Okay. So this is, as you see, these are all written here. So what is the process that we are currently carrying out? Evaporation of water. So you can write this H2O liquid to H2 vapor. This is a phase transformation, but it can be considered as a chemical reaction as well. Okay, it's phase transformation. Okay, this I have already seen. So two examples, but I will take only one of them. This one that I started, because then I will stop here. So start. So initial state. Start. How will you reversibly evaporate water? We see evaporation of water, they are all irreversible processes. The natural evaporation are all irreversible. Finite driving force. As you see, the water is evaporating, okay, from this pond, or you are evaporating from your glass of water, or from the floor, some water actually sprinkle and then it will evaporate away, soon disappear. These are all irreversible evaporation. But reversible evaporation will occur how? How can we carry out this? So starting state. So remember, equilibrium to equilibrium through equilibrium. So equilibrium state. First is water and some vapor in equilibrium. What is the? This is actually this is arranged. Okay, this is actually a chemical process, and I tell you what, at 342 Kelvin, which is 69 degrees centigrade, which is 69 degrees centigrade, 69 degrees centigrade, what happens? Equilibrium vapor pressure is 0.3 atmosphere. For each temperature, there is equilibrium vapor pressure. So we have picked up 69 degrees centigrade, 342 Kelvin, so 0.3 atmosphere. So what is the equilibrium state here? 0.3 atmosphere vapor pressure. And so if you have a cylinder piston arrangement, very convenient to understand. So 0.3 atmosphere outside also, external, surrounding, and system. System is in equilibrium. Start from this point, okay, you carry out evaporation. So what you have to do, unless you change this, upset this value, there is no hope of any process. It is equilibrium, remains equilibrium. That's why it is equilibrium. So we actually do it. This is reversible, 0.3 minus dP. Make it 0.3 minus dP. So the moment this happens, why follow? What happens? So there is an imbalance of pressure. External, surrounding, and system. So what will happen? So it will try to establish that value. So this is sustained. Remember, to write, I write something here. Importance. Sustained means I will keep it or hold it there as long as I wish. Hold there. 0.3 minus dP. Sustained. So what will happen? Since it will try to equalize. So what will happen? It will then expand. If volume expands with the same, then it will happen, the increase in volume, so dV change, dV maybe dV, if I may write, dV volume change, then again it is restored. 0.3 minus dP, come on, come in time, 0.3 minus dP, satisfied. But there is actually one problem. Another criterion is not satisfied. What is that? So suppose it is 0.3 minus dP, but chemical equilibrium requires how much? 0.3, exactly 0.3. So what will happen? Exactly 0.3, it is not exactly 0.3, 0.3 minus dP. So to increase the pressure from 0.3 minus dP to 0.3, some number of moles of vapor must be added, and that comes from the liquid. So dn moles of water then evaporate. evaporate into this space and makes it 0.3 to satisfy chemical equilibrium, chemical requirement. So two requirements are to be satisfied. One is mechanical equilibrium. Mechanical equilibrium means what? P system is P surrounding. Another is chemical equilibrium. What does it mean? It will try to get, what is this? Chemical equilibrium. What is this? To make pH2O is 0.3 atmosphere in the system. In the system. So you see, so first what happens, again repeat. So when I disturb the mechanical equilibrium, initial state equilibrium, all equilibrium, mechanical upset, so then there is a change in volume, increase in volume, then pressure drops, and the moment pressure drops, it is no longer 0.3. 0.3 minus dP. So to make it 0.3, because chemical equilibrium must be satisfied. Right? So dn moles of liquid water evaporates into the space, into this gas space. So it is now 0.3. But then again class, because this sustain, I have not changed it. 0.3 and 0.3 minus dP. So what will happen? So again it will expand. Again it will expand because 0.3 minus dP is less. So further dP. 0.3 minus dP equal, again chemical requirement not satisfied. So again some moles evaporate. So this way, some moles all the time evaporate. As long as this is 0.3 less than 0.3. For reversible, 0.3 minus dP. Okay. So this goes on. How? That means this goes on and dn moles, and integration of dn means finite number of moles. So any number of moles, you can, moles of liquid water, you can evaporate, water, you can evaporate. Any number, full water, the whole of the liquid, H2O liquid, you can evaporate. No problem. Any finite change. So, but you have sustained with this, okay. Now, how to stop this? Suppose you have satisfied. You have been satisfied that, okay, 5 moles of water, liquid water have been evaporated in reversible manner, but you want to stop the process. How will you stop the process? Well, close, okay, suppose you stop the process. So, restore 0.3 and no, say it is mechanical equilibrium, chemical equilibrium, happy, okay. So this happens actually. So restore, then process, restore and process stops. So restore, when you restore means, okay, it is better I don't write here, confusion. If you restore, if the external is restored to 0.3 atmosphere, 0.3 atmosphere, then the process stops. Who likes so? Who wish so? This is actually total. So this is our reversible evaporation, any amount of water. How you can irreversible? This is a reversible. Let me write reversible approach, reversible evaporation of water. So reversible, how you carry out irreversibly? So reversible evaporation of water. So remove this unnecessary. Evaporation of water. What is the external pressure? The external, tell me what will sustain is 0.3 in this case minus dP. irreversible evaporation of water. If you carry out irreversibly, what is the P external? What it should be? What you have to do? How you carry out irreversible, which is simpler? Is finite change, finite driving force, sir. Not infinite. What is the driving force here? 0.3 and 0.3 minus dp means dp. dp is the difference. And corresponding driving force. Pressure infinitesimally small, hence driving force infinitesimally small and satisfy reversible requirement. Irreversible, so finite, any pressure. So call it, how you call this? Any value, how call this? Minus delta P can be 0.1, can be 0.2. So this you carry out. Okay, similarly, the whole thing will happen. This happens actually. This pond actually 0.3 minus dp. This is actually, I can explain you actually how it's evaporated. Atmosphere has a humidity, some moisture, atmosphere, and there is a saturated vapor pressure of the water at this today's temperature. So there is a difference. There is a finite change. So evaporated. We see around all evaporations of water are irreversible. Thank you. With this we have concluded. So introduction, in a sense, it is right. With this introduction and introductory terminologies completed. Notice. So start new chapter. Okay, what is this? Let me write this. Oh, another example I said electrochemical cell. I am not actually taking up actually. So this can be, you will study this later. You will follow the same procedure. Okay, so this same procedure you will follow and you will study later maybe in your electrochemistry and corrosion. Start. So what will start now? Fresh, new chapter. First law of thermodynamics. No. You have to wait, stay for 3 minutes. Then you may. Okay. First law of thermodynamics is what? What is this? The statement is statement. Statement is an equation. The statement of the first law is an equation. Mathematical form is the statement itself. What is that? dq is du plus dw. I tell you, okay, finally that, okay, these or these, I say d. I pronounce d, okay, and this is what? Tell me, del y del x, like say del, okay, so d, okay, okay, del, and what is delta? Tell me, delta. Okay, del is a partial derivative, partial differentiation del. We will discuss this as d. Okay, there is a difference between this and this. This I apply where? For path functions. This I apply for state function. Remember this, okay? Applies to path function. Path functions. And this is applies to state function. So please proceed. This is a statement. Box this. This is the statement. What is dW? dW is right. You know this very well. What is this? Heat interaction. So it is a differential form. Differential form of the first law. Form of the first law. Of the first law. Come on in. Of the first law. For infinitesimal changes. Differential form or for infinitesimal changes. Okay, you know. What is this? Heat interaction. As you know very well, heat interaction between system, this is between, I say between, this is between, okay, between, okay, system and surrounding. What is this? Tell me. Work interaction. Work interaction between system and surrounding. Note the symbols. Note the symbols. Symbols as they are called, okay, or pronounced. Okay. Okay. What is this new? The new entry. This is U is the internal energy. Change in new term, internal energy of the system. Infinitesimal change. Understand? du. Change in internal energy system. Or find given integrated form. Right here for infinitesimal change, right? In addition, additionally, for infinitesimal change, infinitesimal changes. Over integrated form is what? Integrated form means finite changes. Integrated form of the first law for finite changes. Is, I'm writing, I ask you what it will be. It is left to you. You have to answer. I'm writing, I'm integrating as if. Then you know, du will be delta integration 1 to 2. You have to integrate with the limits 1 to 2 u2 minus u1. That is delta. Any change? Right? Okay, delta. Delta u. I'm integrating as if integrating this side also. This term also. So what is this? Anyone? I'll be happy. Good. Not delta q. I'm helping you this side. May help you. This is additional integration of du. Simple. What is it? From 1 to state 1 to state 2? Finite change. It is nothing but u2 u1. You know this. What is this known as? Huh? Okay, no problem. But don't do this. But this is delta q. Why you cannot write? Yes. Yes, let's see. What is this? What is this? Why? What is this? Oh, why I cannot write? Why I cannot write delta q? Delta q I can write, but why I cannot write delta q? I'm writing first. Means q2 minus q1. So what's the harm? q2, state 2, q1. What's the harm? Because it is a small change. Huh? You cannot assign q to a state. They are path functions. They are not state functions. This I said. I just am checking if you have actually remember this. Is okay? So you cannot, but meaning is this: the heat interaction involved in the process from 1 to 2, in the path 1 to 2. As the system moves from 1 to 2, what is the heat interaction? Delta we will not use. We will use, so this is, we use Q. Remember this. Q is delta U plus, this is likewise, this gentleman is same. Finite, okay? This is also, you can give a box as you like. I advise you always start from differential, because integration is no difficult thing. Okay, but don't jump into integrated form. This is my advice. I will follow this in the class throughout this course. I prefer starting from the differential equation and if necessary, then I integrate. But don't jump into the integrated, okay? Oh, okay, this is this. Now what is internal energy then? New thing. What is internal energy? Can I write somewhere here? What is the internal energy U? Next question. Remember, internal. You should be careful about the term internal. So it is internal something of any substance, not external. Okay, so what is this? The potential IE, internal energy IE, U is the kinetic and potential energies. Is the sum of the kinetic and potential energies of a molecule, energy of a molecule, suppose, of the molecules, atoms, sometimes atoms are available, okay, of a, or molecules. Some they are available in molecular form, sometimes atomic form of a substance. Any substance, gas, liquid, solid. So this is actually internal energy. So of the molecules. So it is molecule. As different, see, follow kinetic and potential energy you have come across, but these are external. For example, this is moving. This body is moving. The external kinetic energy. A ball is moving. Another is potential energy. Potential energy in a gravitational field, it has a potential energy. It must be an external field. Then potential energy will apply. So maybe gravitational, maybe magnetic, maybe electric, external. So these are all external kinetic, moving external kinetic. It is here potential energy. Also I call potential is positional energy. I often use the term positional. Means if you change the position, potential energy changes, increases in fact. So kinetic external, as defined from external kinetic and external potential energy, these are internal kinetic and internal potential energy. So note, these are internal, important line, internal kinetic and internal potential energies. As different from external kinetic and external potential energies. Note this. So what is internal? And then next questions are what is internal? Internal, yes, there is also kinetic. Internal kinetics examples are translational. Molecules are all the time in motion. Here, in a gas, in a solid, liquid, molecules are in motion. Atoms, motion. What are the three types of motion possible? Translational, rotational, vibrational. For solid, for example, it is only vibration. For gas molecules, here in this room, the gas molecules are having three things: translational, rotational, and vibrational. Particularly if it is diatomic molecule or triatomic. For monatomic, only translation. But these are the three modes of translation. So translation is over. So what is potential, sir? Internal potential. Internal potential, if there is attraction between molecules. If there is attraction between molecules, then there is potential energy. Again, see, two gas molecules two gas molecules attract each other. So if they come closer, their potential energy changes, positional. And changes means decreases. If they attract, if they come closer, decreases. Like here, like in say external field, say it is potential energy. If come closer to earth, to the ground, potential energy decreases. So follow the attraction, follow the direction of the attraction, then potential energy decreases. So here also attraction decreases. If you actually they are separated, more separated, increases, positional. So this is, so when there is attraction of molecule between molecules, attraction or repulsion you may call, but attraction is actually more important. Attraction between molecules, then the question of potential energy comes. In some system, some kind of gas, I am giving you this, there is no potential energy. You know which type of system? There is no potential energy, no attraction. Ideal gas. Ideal gas actually, these are the things that you actually have now. So can I remove this? So example. So this, as I said, what I said, internal energy, continue. I. Energy is what? Kinetic. Internal energy, internal kinetic, kinetic. Kinetic energy, internal kinetic, internal kinetic. Internal kinetic. Better write internal kinetic. Energy. Energy. How many types? 3 types. What are they? This. What are 3? Tell me. Translational. Can I remove first law of thermodynamics is not needed. We are into this already for a while. 5 minutes. 5 minutes. 5 minutes. 5 minutes before time. Translation and translational, rotation, and vibration. Happy? Very good. For example, solid you have only vibration. Okay, so this is possible, but this we'll see. Okay, this start with three internal kinetic, 3 modes, 3 types. Okay, rotation, vibration, and potential. Again, right? Internal potential energy is what, sir? This is relevant when this is applicable. This is relevant when we consider tell me, when we consider the intermolecular or interatomic, when we consider the intermolecular or interatomic attraction. Interatomic attraction. So this happens. Well, this happens actually so internal means between molecules, attraction between molecules. Atoms. To note, maybe important to note, at least one system is there where there is no potential energy. Means where there is no attraction or repulsion. Okay, I've written attraction. Okay. You want to note? To note for ideal gas. Oh, sorry. For ideal gases. Oh, chops are okay. I have to bring. For ideal gases, there is no potential energy. This is important to note. Okay, but for others, real gas, liquid, solid, all are real system. All are real system. So there is potential energy as well as kinetic energy. This is about these constitute internal energy. So internal energy is actually, as I have told you, internal energy is okay. Translation, internal translation. As I've already given you. Right, once more. Internal translation. Internal. Oh, sorry, I already know. Already written there. I've already written sum of this. Okay. Internal, right? Since I've started, kinetic energy plus internal potential energy. Note this. Okay. This is you. Now, some important points about the first law, not bad. Some important features. Some features. The features are important points. Important points. Some important points about the first law. About the first law. What is it? 1. It proposes internal energy. Okay, 1. What is this? It introduces internal energy. It introduces internal energy, i.e., which is a tell me, state function. Which is a state function as different from, as opposed to work or heat interaction, which are path functions. Which are path functions. This is first point. Second point, interesting. We are interested in changes. We are mostly, to be defensive, to be conservative, we are mostly interested in the changes in internal energy, in the changes in U, not the absolute value of U. Absolute value we may not know. Difficult. For simple system may be possible, but difficult. But we are, fortunately, we are interested in the changes in U. That is du or delta U. Not absolute values. Not the absolute value of U. Absolute, I'm writing here, absolute value of U. This is important. Sometimes we get to know this, we may know this, but mostly we are using changes. Okay, this is the thing. Second, third, can I remove this? Third point here, right, start from this place. Third is, there is a notion that first law of thermodynamics is law of conservation of energy. But we should dispel this confusion. So, the first law of thermodynamics is different from the Law of conservation of energy. Why? I tell you why. Remember, the first very useful, why? Right. Why? Okay. Note the law of conservation of energy, if I may write this way, law of conservation of energy applies to the universe. Applies to the universe. Means system and surrounding together. Means system, that is system and surrounding together. That is system plus surrounding together. Not to system alone. To the universe, not to system. Not to the system alone. But we are interested, but the first law applies to the system. To the system. The system, we can use to the surrounding, we can use it to surrounding, but then we have to treat surrounding as a system. That is possible. Okay? We can, but applies to the system. System, okay? And we are interested, since we are interested in the system, so first law is more useful. Hence, first law is more useful. Is more useful and important. Is important. First law is important. Because why? If it is said we are working with a system. We have some problem, chemical reaction problem. So if it is said energy of the universe remain constant, what will do with this? What shall we do? That is fine. So how does it affect my system? I am producing titanium from titanium oxide, ore. So universal energy constant, so what shall I do? Whether this is a reaction system, this reaction will occur, this system, any comment from the law of conservation of energy? Whether the reaction will occur, or if it occurs, how much heat will be extracted or given, will absorb? What is the answer? From the law of conservation of energy, it says only energy is constant. Universe energy is constant. No more statement, no more amplification. But we are interested in the system. This is a reactor, this much. Universe is actually big, too big. But no concern. Whether the reaction will occur at this temperature, at this pressure. So this is more important, okay? But I can show you. But in a way, however, remember this is the underline. This is different from, and this is more useful. This we'll use. In fact, we'll use the first law, not the law of. This is actually looks sounds nice, but for us, system is very important. Interaction with the system and surrounding is there, but our question will be concerned on the system, because this is my project. This is my objective. Okay, good. So, in a sense, I can get back to it quickly, but in a way, we can arrive at the law of conservation of energy, at the law of conservation of energy from the first law. From the first law. That is very interesting. From the first law. Quickly, this is very Very simple. So first, I'm writing dq system applied to system. First law applied to system. dq system is du system is dw system. This you know, dq system means this is system cannot be interaction is system surrounding. dq system, dq system, system surrounding. Since interaction, this is interaction surrounding du system. Applied to surrounding, same. It carrying a process. This is the heat interaction, and this is the internal energy change of system. Now, treat surrounding as a system. When surrounding, treat surrounding as system. Then you write treat surrounding as system. Then you can write. Change this again. You have a process. System surrounding is interacting. So what is this? This is will be changed. It is system surrounding together. So same. It will be what? How much? Tell me. dq opposite. Okay. dq system. It is better, right? dq system better. So minus dq. Okay. Acha, very good. Very good. Okay. Minus dq means when heat is rejected, it is absorbed. Surrounding is taking up, means plus. When it is plus, it is the opposite sign. dq system, dq surrounding. Write this. dq write first. dq surrounding is du surrounding plus dw surrounding. Right this way, but it is an interaction. But you know, you write dq system, but star, double star. Quickly go to the top. Go to the top. Okay. So, but I'll stop this after this. dq system, teacher is actually waiting outside. dq system, tell me, is minus. This you know though. This is easy to follow. Why? If a system rejects this, who gets that? Surrounding. So positive. So getting is increasing. Okay? Positive. So heat rejected is negative, heat absorbed is positive. So that's it. So it's opposite sign. Always opposite. dq system, and then tell me dw work done by the system means on the surrounding. So dw system is, tell me, is minus dw surrounding. Call it equation 1, call it equation 2. Okay? You can remove all these things. Okay? Remove all this. dq system. This I said system. You are applying first law. Apply first law right here. Apply first law to system, and this you write apply first law to surrounding. Apply first law to surrounding. But it is when you apply surrounding, treat surrounding as system, as I already written. Treat surrounding as system. No problem. So what happens? So from 1 and 2 by 1 plus 2. What you get? Apply. This and this together means 0. 0, see, 0 is du system plus du surrounding plus 0. This is known as, that is du universe. This is du universe is 0. That is u universe is constant. This is, in a sense, internal energy of the universe is constant, unchanged, conserved. So internal energy of that is constant, or constant is conserved. So this is law of, in a sense law of conservation of energy. Okay. So internal energy of the universe is conserved. So this, okay. So this is. So the fourth and fifth, two additional points are there. I will discuss this. So write this. Is constant. This is the law of conservation of energy in a sense. Okay, leave it there. Thank you very much for your attendance and for your stop this now.